Okay, hello everyone. So today we are having the last session of our webinar series, which is titled AraHaul, Multimodal Wireless X-Hole Living Lab for Long Distance, High Capacity Rural Connectivity. Will be presented by Nadeem, and Nadeem is a PhD student in the Electrical and Computer Engineering Department at Iowa State University. He's also a member of YSI Center. He earned his bachelor degree from Bangladesh University of Engineering and Technology in 2017, and he got his master degree from Iowa State University in 2025. And before starting his PhD, he worked for more than 4 years at a major mobile network company in Bangladesh. At YSI Center, he helps lead the design and testing of ARA Wireless Living Lab, particularly the AraHaul, which is a wireless X-Hole test bed for long-distance, high-capacity communications. So his research is focusing on building strong and high-speed wireless networks using microwave, millimeter wave, and free space optic links. With that, I will give the floor to you, Nadeem. Please start.
Thanks, Professor Selim, for a nice and kind introduction. Today, for this session, this session is about an AraHaul, so a multimodal wireless X-Hall living lab for long-distance, high-capacity rural connectivity. My name is Amdi Nadim. I am a graduate research assistant in YSI. So let's start actually. So here is a brief outline for today's session. So we are going to talk about all of them like briefly. So first, the rural broadband challenge. So in even like nowadays, rural broadband remains one of the key connectivity challenges. So although rural USA includes like 72% of the nation's land and around 46 million people lives in rural regions. Despite ongoing efforts, like 39% of the rural US population and over half of the global rural population still lack reliable broadband access. Agriculture dependent regions are especially affected. Many farms remain completely disconnected. So, in particular, given that rural towns are usually tens or even 100 miles away from one another, and that many rural towns and agriculture farms are far away from their nearest internet backbone connection points. And this issue is compounded by the high cost of deploying fiber-based XL infrastructure in low density areas, where return on the investment is often too low for commercial viability. And moreover, obviously, geographic isolation further limits access to the nearest internet backbone nodes, making it even harder to connect these communities. And lastly, current commercial wireless technologies like microwave and millimeter wave have limited capacity. Microwave typically offers only 1 to 1.5 Gbps, while millimeter wave links can like provide up to 10 Gbps, but only for a short distance, around 1 to 2 miles. So, what kind of innovation, research opportunities rural and agriculture regions can offer us? Actually, rural areas provide us the opportunity to realize the rich and diverse use cases of advanced wireless and rural broadband technologies. So when you look at the actual use cases emerging in agriculture and rural operations, the requirements span nearly the entire performance space that any modern network has to serve. So starting from the lower left, where we have the IoT quadrant, so things like soil nitrate sensing, grain bin monitoring, like livestock health tags. So these are low bandwidth, latency tolerant workloads. They are cheap to support. They are cheap to support individually, but but they scale into thousands of endpoints per farm. Then Moving up to the video quadrant, so we get bandwidth hungry but still latency tolerant applications like 360-degree livestock monitoring, AI-driven crop scouting with mapping from imagery. So this push tends to hundreds of megabits, often in a brushy pattern tied to field operation. So, and in the lower right, the system control. So the system control like includes autonomous precision planting, UAV monitoring, grain mill process control. So these don't need much throughput, but they demand tight and predictable latency because there's a control loop involved. And the upper and then in the upper right, the most demanding quadrant, extended reality. So XR teleoperation of unmanned ground vehicles, XR based troubleshooting of farm equipment, then livestock telemedicine. So this application needs actually high bandwidth alongside with low latency simultaneously. So overall, these slides demonstrate that future rural communication networks must support a very wide range of requirements simultaneously, from low power IoT sensors to high speed XR and autonomous system. So it also shows why advanced wireless and XR technologies are becoming increasingly important for enabling smart agriculture, automation, and resilient rural infrastructure. So these slides actually highlights how rural areas offer a strong rural first advantage for piloting advanced wireless and broadband technologies such as 5G and future 6G networks. So agriculture presents rich and diverse high impact use cases, including autonomous tractor, drone coordination, and real-time edge analytics, and wireless teleoperation of ground and aerial vehicles that require both high bandwidth and ultra low latency. So because of large operating spaces and real operation needs, rural environment provide an ideal test bed for validating next generation connectivity solution for wider deployment. And to meet all these diverse requirements, a rural XL network has to be engineered to handle these full spread use cases, and crucially, it has to be handled reliably. So often over long distance in weather conditions that urban deployments rarely see. So there's the design challenge we'll be unpacking in the rest of the talk. So as I mentioned earlier, to tackle all these rural broadband challenges by leveraging all the opportunities, advantages that rural regions can offer us, we build ERA, Wireless Living Lab for smart and connected rural communities. So what is ERA actually? So ERA is an at-scale platform for advanced wireless research being deployed across the Iowa State University campus, city of Ames, where like ICU resides, and surrounding research and producer firms, as well as rural communities in central Iowa. It serves as a wireless living lab for smart and connected rural communities, enabling the research and development of rural-focused wireless technologies that provide affordable, high capacity connectivity to rural communities and industries such as agriculture. So ERA is a part of National Science Foundation platform for advanced wireless research or power program. So and ERA stands for agriculture and rural communities, obviously. And in astronomy, ERA is a southern constellation of stars. So if you can see this image at the corner of this top image, the image of ERA actually shows the way rural wireless is expected to look like. So with this disk like wireless access network connected by long distance wireless backhaul. And these lights in the sky from the ERA stars also signifies the vision of ERA as the light for rural wireless and broadband. So In order to leverage such rich use cases of rural and agriculture regions, the ERA deployment covers a diameter of over 30 kilometers. So with base stations providing coverage for residential, crop, and animal farms. And the base stations are interconnected in a mesh network by high-speed wireless and wired backhaul technologies. So we have deployed 7 base stations so far in 2 phases. In our first phase, we deployed like 4 of the base stations in residential building, like students' residential building, that is Wilson Hall, Agronomy Farm, and the Curtis Farm, and on Research Park. In our second phase, we have deployed like 3 more base station, Boone, Gilbert, and I6 Tower. So in this map, the vertices actually mean the base stations, and the edges that's connected to vertices, these lines, it's actually the wireless X-Hall link. And uh, in our third phase, we are going to deploy this info bunker base station very soon, and the rest of the base stations will be deployed in near future. Alongside with the 7 base stations, we have deployed 34 UEs so far, and 16 more UEs that are user equipment are yet to be deployed in different UE sites. So now move forward to the ERA deployment. So here is some of the glimpse of ERA base stations that has been deployed in at Wilson Hall Agronomy Farm. So we have like Wilson Hall is a residence hall structure, and the base station was deployed on the top of a residence building. Then we have like Agronomy Farm and Curtis Farm. Those are like a monopole structure. Now we have deployed our base station on the top of Research Park. And for Boone, Gilbert, and I6, we have like shared the commercial tower, telecommunication tower. And for the UEs, we have UE deployed our user equipment boxes in different public and private properties, actually, for the convenience and for the benefits of the public. So we have like UEs deployed in Cyrite, in different ag vehicles, on the water tower, in the middle of different agricultural farms like Curtis Farm, and so on. So, right now we will talk about the Era Wireless platform. So, Era Wireless platform is mainly includes like 2 major platforms. First, the AraRAN platform. So AraRAN is a high throughput coarse and SDR system. So it has like a MIMO and SDR RAN platform. So the Era MIMO TV white space, it has like Era MIMO TV white space that is provided by Skylar Technologies. Era has like Era MIMO C and millimeter wave band that is provided from Ericsson, and we have also Era SDR platform. And the second one is the AraHaul platform itself, which we are going to discuss in detail into the session. So what is AraHaul? So AraHaul is the multimodal wireless XL testbed for studying long distance, high capacity communication. So AraHaul is a part of the Era Power Wireless Living Lab, feature state-of-the-art XL platforms that operate at diverse frequency bands ranging from microwave and millimeter wave operating frequencies respectively 11 gigahertz and 80 gigahertz to the free space optical communication, that is FSOC, known as Air Optical, and operates at 191.7 to 194.8 terahertz frequency and provide communication capacity up to 160 Gbps across distances up to 20 kilometers. And AraHaul also includes LEO SATCOM. So we have Hughes and Starlink IDU and audio terminals deployed on the Wilson Hall base station. So, building on the contribution to the deployment and development of the Era Wireless Living Lab and wireless Excel system like AraHaul, I would like to highlight the motivation behind our efforts, specifically why we need a new Excel solution for rural broadband. So, as I mentioned earlier, rural broadband remains one of the key connectivity challenges even today, and it's and the for the rural regions or agriculture farms, the nearest internet backbone is kind of like far away, and obviously. High deployment cost for the rural-based XL network is a major issue. Then geographical isolation and the limited communication capacity for the traditional links. So those are the main reasons why we need a new XL solution for broadband. So we have deployed a total of 7 AraHaul microwave and millimeter wave links along with 2 Ara optical links to interconnect 5 base stations so far. So the 2 Ara optical links are deployed from Wilson Hall to agronomy farm during phase 1, having a distance of approximately 6.5 miles. And recently, we deployed our second Ara optical SISO link from Wilson Hall to Gilbert, extending the operation distance to approximately 7.8 miles. And among the, sorry for that, and among the 7 AraHaul microwave and millimeter wave links, 4 links use Aviate WTM4811 radios with the distance ranging from approximately 4.75 to 7.75 miles. So these radios integrate 2 different microwave channels and 1 millimeter wave channel within a single box architecture. And the remaining 3 links having distance of like 7.7 miles, 11.5 and 15 miles utilize MBXD technology to provide long distance high capacity connectivity solution. So this MBXD stands for multi-band cross diversity, and it's also referred to as a dual box solution. So it consists of 1 microwave radio and 1 millimeter wave radio, where each radio can operate on 2 frequency channels simultaneously. So therefore, like a single MBXD link effectively supports 4 concurrent operational channels, enabling an aggregated capacity of up to 10 Gbps. So now we can talk about the AraHaul system architecture. So each base station is equipped with a data router that acts as a gateway for the AraHaul system, data plan, and a management switch for the management plan, ensuring seamless connectivity and management across endpoints. And to support continued research for the AraHaul links, both millimeter wave, microwave, and AraHaul optical links are also connected with the base station host computers, which makes the system remotely accessible for experimental studies and data collection. And so both AraHaul microwave, millimeter wave, and Ara optical software frameworks are designed to manage and coordinate all the system components to ensure robust link stability, operational reliability, and to support for experimental research. And to manage the architectural complexity of our Era system, we designed and developed the AraHaul microwave, AraHaul millimeter wave API, and Era optical API frameworks, and extensible uh, unified interface that expose control and measurement capabilities through RESTful APIs. And the API framework allow researchers to perform advanced experiment studies through container-based resource allocation using the Era portal. So in brief, this software-driven architecture transforms overall AraHaul platform, including like AraHaul microwave, AraHaul millimeter wave, and Era optical into a powerful test-bed-ready research tool, bridging the gap between the theoretical exploration and real-world deployment. And now we will conduct some of the hands-on tutorial. So first we can discuss briefly the experiment workflow. So obviously the Era user needs to log into the Era portal using their credentials. Then they first need to do the resource reservation, then create the experiment container using the user manual, and then conduct the experiment and do the data collection. And after when the experiment will be done, the experiments needs to delete the container and release the resource for the other and release the resources for the benefit for the other persons to use it. And after that it needs to be locked out from the portal. So we have like in total 19 example experiments listed in our Era user manual. So, and for particularly for AraHaul, we have like 5 experiments: 2 for microwave and millimeter wave, 2 for free space optical link, and 1 for satellite backhaul link. So we are going to do some live demo experiments right now. So let me share the. So right now we will go to the Era portal. Uh, Okay, let me share it once again. So this is Era portal. I have like logged in the Era portal before to like save time for the reservation purpose. So I have already like reserved 3 of the base stations. Previously the Gilbert one, Agronomy Forum, and I6 one. So but still I will create a lease for the Wilson Hall and show how to create the lease. So first we need to go to that reservation tab, and from here we need to create a lease for the Wilson Hall. Let's say I will like create the a lease for Wilson Hall. So this is Wilson Hall. So now we can like actually specify the start and end date. If we don't, then our lease will be terminated like automatically after 5 hours. So then here we need to select the sites, like which site. So as I'm going to create the list for Wilson Hall, I will select Wilson Hall here. So resource type, obviously the AraHaul. We are going to do the experiment AraHaul. And for the experiment, we need to reserve the host computer of that base station. So it's already been selected here, the host computer and device ID for all the for the host computers for all the base stations. The device ID is like 000. That can be also found in this resource overview actually. So if you see the host computers is also kind of can be found here, all the resources. So so here I have like already like created the lease for Wilson Hall, and it's still pending. So, and if we just kind of refresh this page, and it becomes active. So I have like created the lease for all the four base stations, which I need to use for our AraHaul experiments. So after resource reservation, we need to go to this container tab. So from that container, we need to create we need to create the container accordingly to our experiments using the Docker images. So here I will go to the container creation. So I need to give a name. So let's say I will give like first we will go to do the uh, first experiment of the wireless XL, that is aviate link configuration and status check. So I'll just name it as Wilson Hall Experiment 1, and I need to use a particular Docker image to create the container, which can be found in this user manual. So I just copy pasted this one. So this is this is the particular Docker image we uh, need to be used to create the container for the first experiment. Uh, then after that, okay, we can give a host name. Let's say, and most importantly, we need to select the exact lease from this drop-down menu of the lease name. So I am going to use the Wilson Hall. That's why I need to select Wilson Hall from this. So it actually means the resource, which resource I am going to use for conducting the experiment. And after that, I need to like select a network from here. So for the experiments, I need to select this error shared net, this network. This network will assign a floating IP to the container so that I can do the experiment in using the error network. So here, so my container is creating. So if you can see the status, like it's still creating. So if I refresh it, so yeah, it's already been created and it's running. So then I need to create another two containers because I'm going to use uh, like for the AraHaul experiments, we need to create containers on different host computers because it has like the link has two endpoints. So that's why like first I create the container at one endpoints, that is Wilson Hall, and now I'm going to create the container at the other end, that is let's say I'm going to use this Wilson Hall and conduct the experiment on Wilson Hall to agronomy firm. So I need to create container on both of the host computer at both base stations. So let's and, we just need to do this. We just need to use the same Docker image to create the container. Then let's say SP1. From here, as I am going to create the container on agronomy firm base station, I need to select the agronomy firm lease for that. And same as previous, we need to select this Era shared network and create the lease. So here is my second lease. So I can just refresh, and if I refresh, yeah, it's running. And for the third, if I want to conduct the second links experiment as well, I need to create another container at i6. So I just create this one a little quick. Okay, so right now I have like created the container in three of our base stations. So let's say, so here is my container. So it's you can see these IPs, all the container details here. So these are the IPs actually, the floating IPs that is been assigned to this particular container. So we need to go to this console. We can like, or now we can just use the instruction. We can follow the instruction from this user manual. So first, let's say we need to select a link to run the experiment, right? So first one is link one. So how can I select the link? So for that, I need to use this command. So let's see. Source link says link one. So I'm going to do the experiment on link one, which is Wilson Hall to agronomic firm, and it's use a like single box a radio solution where like millimeter wave and microwave frequency are co-located. So I have already selected link one. So now I can check the radio status. So here are some comments like some comments are actually listed in the user manual to check the real-time status of the radios of the link. So first I am going to check the status, real-time status. So carrier 11. So if it's carrier 11, that means it's the microwave link. So first I'm going to check the status of the microwave link, and if it's if there is a like mmw in front of this carrier, that means like the millimeter wave link. So let's see first. So because like when we are trying to execute this command, is trying to log into the radio, and then is facing the fetching the radio status data from there, and it will show here. So sometimes yeah, there is some latency. So right now we have that carrier status data. So if we go through this status check, so we can see, okay, this is the Wilson Hall to Egg Farm radio from phase one. So, and this is the Wilson Hall end. So this data we are getting, this status data we are getting is from the Wilson Hall radio, and it is directed to the Egg Farm one. So if we
Hey
can go through,
Naveen,
so yes,
can you zoom it because the text is not that visible?
let me try. I think I need to zoom. Oops. Now the console actually has
Yeah,
become
it's readable now. Yeah.
okay. I see. Thanks, Sarah. So if we go through the status data, so we have like we have first one the operational status from both local end and remote end. So it's up means okay, the link is up and it's active. So and then we have like bandwidth, like what is the configured bandwidth for this link right now. We have the TX and RX modulation. What is the modulation? It's already been like configured. And then what is the current TX power? We can also see that TX-RX frequency. So for each link, we have we have a like licensed frequency from FCC. So after doing the analysis, like interference analysis and also the loss analysis, we need to like submit it the submitted to like we need to get this frequency for particular link through FCC after FCC's approval. So and we can also check what is the theoretical capacity for this link using this condition, using this configuration and under certain weather conditions. And for the real-time measurement, we can also see the SNR, like what is the SNR value at the local end, and also what is the SNR value at the remote end. And we have like the RSL values as well. So this is the real-time RSL value. So if we execute this command again, these RSL values will be changed. And we also get the fade margin, beta rate, and some how and how many bytes and what is the number of bytes that is has been corrected so far. And need to be refreshed. So as I mentioned earlier, so if we just run this, execute this command again, the RSL values will be changed. So it will give the real time actually RSL and SNR readings. So yes, so here is the so previously it was minus 44 point something dBm. Right now it's minus 45 point something dBm. So it's depends. It's actually real time readings, and we can also check. Like I am running the experiment at Wilson Hall end. Right? So if I execute this command, I am getting the data from the Wilson Hall radio. And I can also fetch and check the data from the remote end at Wilson Hall Radio. So my remote end is ECFARM for link 1. So I just need to use this remote flag to fetch the data from the other end or the remote end radio. So if I just execute this command, yeah, it will take some time, so obviously, to fetch the data and show in this call, like CLI. So just to show, previously it was, okay, I have that data. So first we checked the status from Wilson Hall end, which is my local radio end, right? And this is Wilson Hall. And right now, after using this remote flag, I will get the data from the other end, which is the ECFRM end. So right now, the data is showing is from the ECFRM radio, and it's pointed to Wilson Hall. And yeah, obviously, it will give the same status. So the operational status both from, and for this, like for ECFRM, the operational status means like the ECFRM status itself, and the remote operational status means, okay, it's the status from the Wilson Hall. And similarly, we can check the microwave. Oops, sorry for that. Microwave carrier status as well. So millimeter wave link status as well. So obviously, yeah, this is the millimeter wave link, and as I used that remote flag, so is this status is from the ECFRM radio, and you can see like the bandwidth. So millimeter wave is a high capacity. Millimeter wave has higher capacity, like much more higher capacity than microwave, and the bandwidth is much more higher. The bandwidth of this millimeter wave is mm, 2 gigahertz, and the TX RX modulation is configured as QPSK, and TX power, we can also check the TX power and the TX frequency as millimeter wave, like the central frequency is kind of like 80 gigahertz, so the TX RX frequency will be around, it will be ranged from 71 to 86 gigahertz within this range. And yes, we have the real-time SNR and RSL values from both of the sides, uh, from both ends. So right now, first we just checked this radio status from link one, which one was Wilson Hall to ACFARM. Now we can actually check another link. So what I need to do, same as before, I just need to go source set link dot sh, and I need to select the second link. So I select the second link, link two. Now it selected the second link to conduct the experiment. So same as before, I will just save some times, just like going up. So first I can check the microwave carrier status. It's taking some, okay, it's fast that. So as I mentioned, link 2 is from Wilson Hall to I6. Now we are getting the data. We are getting the radio status data from Wilson Hall to I6. So you can see the from this name. So this data is from the Wilson Hall end, and this radio is directed to I6. So we can obviously see the status of all of them, like the operational status, bandwidth, TX modulation, TX frequency, and real-time SNR and RSL values. So just to check another, right now we will just check, execute another command, that is millimeter wave for the remote end, and then we will move to the second experiment. So actually the first experiment is all about like getting the real-time radio status data continuously. So we can like uh, we can just generate a script or create a script to run these commands in a time interval, so that it will fetch all the data from the radios, and it can like store in a CSV file to in a continuous manner. So here is the radio status data for millimeter wave carrier. So as I use the remote flag, so it will fetch the data from the I6, so which is the local end for this command. So, and we can also see the I6 radio status data, the SNR and RSL values, real-time SNR and RSL values. Okay, so this is about the first experiment. Now we will go to the second experiment, which is about the ambient link throughput and latency check. So for the second experiment, we need to create the containers again, and using a separate Docker container image. So we just need to follow the same procedure. We need to, let's say I am going to do the experiment at Wilson Hall for the second experiment. And there I need to use this particular Docker image. So let's see. 7.2. I need to yes, as I'm going to use Wilson Hall, so the list I need to select Wilson Hall, and from here the Era shared network, and create the container. Same as I need to create container. So this one I need to create the container at agronomy farm as well, because I'm going to use the first link. And here I need to select agronomy farm, this one, and this click selected. So right now I have like containers created for the second experiment. So first I am going, so we are going to do like same as this experiment for two links. First I am going to do the experiment for Wilson Hall to Egg Farm. So I'm going to that container, this console. Okay, so it's ready. As first step, so this is about the throughput and latency check. So for throughput, we are going to use the iPerf tool, and for latency, obviously we will go to the ICMP, go for the ICMP. So for that, first we need to check what is the IP address assigned to this container. So for this IP address, that we need to check the IP address, which IP local IP address is attached to this container. So how can we check that this IP address, this command, and from here we can see this IP has been attached to this container. So for this throughput and latency check, like mainly for the throughput test, we need to uh, select one base station as a server and another one as a client, so that we can like transfer the data through the Aviate channel, right? So same as I have like another tab open here. I'll just go to the container and this console, and I also check the IP address. It should be in the same network. And yes, so here is the IP address for the Ekron container 192.168.0.2. So if and previously, and it's assigned 192.168.0.128. So first we can check the latency or the ping. We can do the ping test. So just inactive. So we can do ping.192.168.0.2. If I remember correctly, that is the IP address assigned to the egg farm. Yes. So we can just do the simple ping test, and yes, so the link is up and it's pinging. So we have that latency data from this ICMP test. So now I am going to move to the second part, that is the throughput testing. So we are going to use the iPerf tool for do the throughput test. So I will let me check the IP address one little quick. So this is 192.160.128. That is the IP address. So I'm going to set this Wilson Hall as the server. So iPerf3 as the, and I need to go 168.0.128 as the server. So my server is set up. And I'm going to make this egg farm. And I'm going to make this egg farm as a client. Eight. So if I run this iPerf, it should work, and we can actually see this is the like real-time throughput for this link. Like what is the real-time throughput? If we want to run it continuously, we just need to use this command. Then this iPerf test will run continuously. So we can see it's actually varying depending on the real-time throughput actually varying depending on the weather conditions and all this stuff. So right now we are getting like around 3.25 Gbps. It's based, obviously, it's based on the configuration. If we configure the link in a higher configuration, we will get more throughput. So this is all about the second experiment, but we are going to do another one for another link. Let's say I am going to do the same experiment for Wilson Hall to I6 link. So for that, we need to just create the container for Wilson Hall for Gilbert. Let's say that I'm going to do the experiment for Gilbert. First, I need to create the container at Gilbert. Yeah, and I will create another container at I6. So I need to use this I6. I need to select Ara shared network and create the container. So my containers has been created actually. So this Gilbert experiment 2, this one I'm going to use Gilbert to I6 link. So I am going to, okay. Is it still created? Yeah, it's created. Okay. That's good. So I'm going to use another link like Gilbert to I6 link to do the same experiment, this throughput and latency experiment. So this link is around 8 miles long. So, and it has both microwave and millimeter wave. So in the throughput, we will see the aggregated real-time throughput or bit rate for this link. So first, same as before, I need to check the IP address. This is 192.168.6.128. And I also need to check the IP address here. This is 192.168.6.2. So just to make sure the link is working, I need to ping it first. 6.128, if I remember correctly. And yes, so this is the real-time ping and latency result. So it's the latency is much less than Wilson Hall to ACFR. And now we are going to do the same thing. So I will just set up this one as a server, hyper server. So let's start 2. Okay. I have already set this as a server. And now from here, I will set. Cannot console. Why? Let me see. Oh, yeah. So I got 3, 168.6. If I remember correctly, this is 2. So 2. Let me run it continuously so that we can see that. So and yeah, so if we can see this link bitrate or throughput is much higher than the first one, because and this is more stable link in terms of the infrastructure actually. So we are like continuously getting more than 7 Gbps in real time. So yeah, this is the actually real time throughput test from the give birth to I6 link. So these are the two experiments we can conduct on the aviate links. First one is the status check, which will give us the real-time SNR RSL values alongside with the configuration. And the second one is the throughput and latency check, which will provide us the real-time bit rate and also the latency information. So everything is kind of like added in the Era user manual. So if we just follow this instruction step by step, we can able to do the experiment using our Era portal using these AraHaul links. So now I am just go to so these are the two experiments we are going to do today. So let me go to I go back to my presentation. So, and I will just share some of the, I'll just share some of our previous observation from our experiments. We are
So,
already,
Nadim, can we make this very quick because we are almost out of time? Okay.
yeah. So, yeah, I'm almost done. So, yeah. So, some of the performance characteristic, I'll just go through very quick on this. So, we have like observed previously like the weather impact on the air hole. So from our observation, we saw that yeah, microwave links are very microwave links are very stable yeah, in rainy condition rather than the millimeter wave link. And we have also seen some of the like spatiotemporal diversity, do some analysis on the spatiotemporal diversity among our 7 links because they are like spatially diverse. And these are some of the result, some of the like time series result from that spatiotemporal diversity. And for the air optical, so for the air optical, as mentioned earlier, air optical is more susceptible to the weather conditions. So we have we have actually we can say updated and upgrade our system using different kind of technologies such as a low noise amplifier, that is the LNA, that helps us to keep the risk RX power level above the threshold all the time. And the air optical is susceptible. So in a clear condition, the air optical will work. So if we see, so this is the beam actually captured in the CMOS camera. So without no rain, the beam is like very clear, but with moderate rain it's become dim, and with heavy rain there is no beam. We can't see any beam captured on the CMOS camera in the air optical system. And for the air optical, so we have like achieved 2.92 Gbps on a single 10 Gbps channel so far, but we can scale it up to so we have like 16 channels in air optical, right? So it can be scaled up to um, like 50 Gbps. If we just get this same result for each channel, it can be scaled up to around 50 Gbps, like for one link. And there are some more like innovation and more technologies in air optical. So those are kind of we can use the coherent transceivers. So each coherent transceivers is around like 100 to 400 Gbps. So if we can use like 16 channels with our full potentials using these coherent transceivers, we can get around 1.6 to 4.2 TBps, that is terabyte per second in one air optical link. But obviously there are some engineering engineering challenges, and there are some additional optimization challenges related to both weather and the system to make it happen. So, and for AraHaul, like Era-enabled AraHaul research, so AraHaul can generate a highly rich real-world dataset incorporating like actual weather impacts, which can be leveraged to develop advanced high-capacity intelligent wireless EXO platform planning frameworks and pave the way for the multi-scale, multi-dimensional modeling and analysis research. So uh, with saying that, this is the like end of my today's session on AraHaul, a multimodal high-capacity wireless XOL network. So here is some of the reference for us. So we have like Era portal, Era user manual, and we have like Era office hours every Tuesday, 5 to 5:30 p.m. At US Central Time. And for any kind of help or issues, we have like email addresses for help and issue support. And thanks everyone. That's all for today's session. Now I will happy to answer any questions if you may have. Thanks. Thanks everyone.
Thank you, Nadeem, very much. So questions from audience? Martin, please go ahead.
Yeah, thanks, Nadeem, for the talk. I kind of want to go back to the architecture picture you had on your slides that showed the management and data networks with AraHaul.
Yes.
Yeah, this one. So you know, from the experiment for doing sort of the latency and throughput, it seems like each link is sort of segmented right now, where you couldn't do, say, multi-hop testing. You'd have to do the routing through the host computers to do some maybe multi-hop sort of experiments.
Right.
But the thing that I guess I haven't quite wrapped my head around yet using Ara is, I feel like I only have access to the management network. I don't know how to access that data that sort of data switch to do the routing. But maybe it's just a misunderstanding on my end.
So yeah, thanks Martin for the question actually. So right now we have the experiment only for a single link. It's only for the single hop. We haven't like we are still working on the mesh network experiment that is like multi-hop, what you are saying, so that from the portal we can like select two nodes and it can be and the data or data can be routed through the mesh actually, and we can check the throughput test. So it's not been published yet. We are going to like publish that experiment really soon.
Okay.
So
okay, cool.
Yeah.
Thanks.
Any other questions?
Yeah, any other questions? If not, okay. Thank you very much for coming today, and thank you very much, Nadeem, for your presentation. And soon we are going to announce for any new talks. Just like the only thing I can advise, just look into our website. I also put the website in the chat. I added all the videos for previous webinars, and also this webinar, once the video is ready, it will be added to the website and also added to our YouTube channel. Thank you very much, everyone.
Thanks everyone. Thanks for joining.